when Roshan's panel was getting going, I'm thinking to myself, new construction sounds pretty easy. All we got to do is get the design team to think about it. And retrofit, this is the hard work, right? And so that was my whole narrative. And then halfway through Travis, I was like, that's out the window. It's obviously plenty complicated. But it is a different world, new construction versus retrofit. I often make the analogy that new construction is curing cancer, and retrofit is the emergency room, because it's a shorter timeline. Things happen more quickly, maybe 90 days, order of magnitude. And of course, things are measured in years when you're talking about building a really complicated space, such as the ones that we heard about. So we have 5 projects represented, and what's going to happen is each of the speakers is going to go through their circa 10-minute background. It'd be a good idea to jot down questions, and I'm certain that there's going to be a lot of them at the end. So the first one to go is Tom Tribble from Northwest Labs.
So we've had the benefit of some really strong presentations. Focused people, worthy projects, fundamentally brilliant. Retrofit is often not so much brilliance, or it has to do with basically dealing with existing situations, and it sort of happens without a plan. So I was asked to put together a few words of wisdom, because I guess Northwest Labs is considered a positive project in the Harvard portfolio. And what I learned during running and managing that project was the first thing you need to do is challenge assumptions. In other words, look at the fundamentals, figure out what you're going to do, and then persist, and then persist some more. So what am I talking about? Go back to 2007. I was in the enviable position. This building had just been completed. Somebody said, Tom, we've chosen you to operate and maintain this building. It must be good to be you. And indeed it was. It was a new building, 510,000 square feet, very attractive inside and out, lots of good positive things, interesting people to work in the building. 20% of the space is laboratory space. And so I enjoyed sort of halcyon days for about a month. And then our green team basically started publishing some data. They weren't headhunting. They were asked to do this, and they put together some information. Somebody, I remember, it was basically Yale said, we're going to save energy. So Harvard said, yeah, we're going to save energy too. Where's the energy? And they basically said, well, if you look at these graphs, most of the energy is in the lab buildings. And all of a sudden, my world started getting a little bit smaller. Then they weren't satisfied. They had to go a little bit further and said, where in those buildings, in those lab buildings, is that energy going? And 2 of these buildings, Northwest Labs was consuming about 19%, and another building in my portfolio, Lisa building, we were in the top 3. So when you stand out in an unflattering way, nobody has to speak to you. You know intuitively it's time to do something. So what do you do when you got a problem? You go to the wisest guy you know. In this case, it was Professor Emeritus Fred Abernathy, and he said, literally, he said, go out and seek energy reduction in the air. And he started reaching up in the air like there was dollar bills. Swear. He's a brilliant guy, but a little bit eccentric. So what does that mean? Well, the building's 510,000 square feet, and we sent out a team to do some air balancing, took some measurements, well, not balancing, just measurements. And the building, as built, as delivered, as turned over, was delivering 12 to 24 air changes per hour throughout the building. I mean, essentially, there wasn't a space in the building that you could go where you didn't hear ventilation noise. You could say, well, maybe that's indicative of something. So the first question that you have to ask yourself, what is that air worth? And that was an interesting problem, because depending upon what system, whether or not there was energy recovery on it, what factors you included, you could get a cost of a cubic foot of air anywhere between $4 a CFM per year to $18 a CFM per year. We wound up settling on a combined average with our energy team of about $10 a CFM per year. And you have to remember that this air was being controlled by 500 Siemens valves at an average cost, material cost of about $2,000 per material valve. So we said, well, what makes sense? We went to our EH&S people and said, we've got 12 and 24, and they said, well, if you were down around 6 and 4, that would be really good, Tom. And I said, fine, we'll do that calculation. So we did a little bit more, and we said, is the volume air changes per hour, is that based on straight geometric progression, or can we do a calculated value? In other words, take advantage of the fact that there's equipment, ductwork, so forth. Turns out we hired SMD, Steve DiGiacomo, and he said on average your lab spaces are about 1/3 taken up by other stuff. And so when we did our tabulation for doing the rebalance, we based it on the lower air volumes, or volume of the space, so forth. So then the question came, the first question that comes up is, how much money can you save if you do anything with this? So we knew what the air changes were, what they went to be. At that time, we had recently hired a continuous commissioning group called Symmetrics. They basically said, we can tell you what you're using now, what it's costing you to ventilate your building, heat, cool it. And if you go to these revised ventilation rates, we can tell you that number too. And I said, fine, what's the number? And they said, $1.3 million. I said, what? They said, $1.3 million. I said, one more time. I said, $1.3 million. Got my attention. But what I did was, being legally trained, one of the things that you have to do when you're trained, you basically, who can I blame? So I went to the engineers and I said, what's up with you guys? You know, why didn't you give us six and 4 air changes? 6 occupied and 4 unoccupied. And they said, we did. And of course they're going, eh. So the problem was, EH&S said 6 and 4. The engineers said 6 and 4, but we had 12 and 24. So I gave the order, change it, right? That's what you do when you're the boss. You say, make it happen. And naturally what came back was, Captain, we can't do it. Actually, it was Tom, it wasn't Captain. It's all right. As you've heard from earlier speakers, basically once you start getting into very low flows, the air valves, or some air valves, don't perform very well, and these didn't perform at all. So basically the question was, it was sort of like, you know, well, can't get there from here. First bump on the road. So I'm an old steam engineer, and one of the things you know about piping is if you need to restrict flow in piping, you put in an orifice. So I said, let's put in an orifice. And they said, oh, I don't know if we can do that. And of course, we did. We put in an orifice. Oh, 1 minute. Put in an orifice, it didn't work, it was loud. Put in a different orifice, it didn't work because it was too deep in throat. Finally, basically what we did, we went through several different iterations, and we came up with a modification. We tried drilling holes in the plate. That worked, but that was very cost intensive. Our machinist came up with this design with the trefoil or the foil type blades and so forth. And that was cost effective. It was substantially less than $2,000 to replace the air valves. We had control, it wasn't too loud, it wasn't too expensive. So we said, maybe we should talk to Siemens before we modify the air valve. Good idea. They supplied the air valve. So we talked to them and Siemens said, no, it's just not going to work. I designed that valve. What you're talking about, it's not going to. So, problem was, you know, we had invested this time and effort, and we couldn't just quit. So we said, well, go ahead. Go ahead. We'll give this a try. We took a lab and we modified the air valves, and lo and behold, it worked. So basically, you know, it's a matter of saying failure isn't an option. You just have to persist until you finally and eventually succeed. And then we got Siemens back in and we showed them what we did in the lab, and they said, yeah, I guess it works. So I went to my boss and I said, we need $625,000 to modify these air valves and put in occupancy control, occupancy sensors, scram valves, and so forth, everything to do the job. And he said, you know, how much money to do what? But basically, it was very successful. We saw the financial gain. You know that you are achieving energy success when you have your utility company coming into your building, rapping on the meters and looking for the bypasses that you've secreted away someplace. And my boss basically, as a result of this, he said, you know, $1 million here, $1 million there, pretty soon it adds up to real money.
If your presentation was longer, I would have loved to, you know, yielded at least 5 minutes of my presentation to yours. I was quipping to some of my colleagues earlier that I've been tried and convicted of putting together pretty much the most boring PowerPoint presentations ever. You will not see any histograms or flying charts or cartoon characters, but myself and others stand in the way of, I think, refreshments, beer as it were, and some networking, so we'll try to cruise through this. So the title of the talk is Whole Building Retrocommissioning, at the BU Photonics Center. Try to figure out this device. So I do have one pretty picture, that's about it. It was built in 1995. I think the sign on the front of the door says 1997. But think about what the computers were like for folks who remember Windows 95, right? This is approximately a 300,000 square foot building. You'll notice a 2-story mechanical penthouse where kind of all the magic is, you know, in this building. It's very mixed use, and that's a key element of this facility. Certainly there's wet labs, a lot of chemistry, but it wasn't always so. Over time, it shifted to wet labs from dry, you know, optoelectronic labs. There's certainly clean rooms, MEMS, micro-nano systems manufacturing, as well as a whole assortment of electrical engineering, mechanical engineering classrooms, and professor offices. One thing that's not in my talk, so I'll make it a part of it. Notice how it's right up against the pike, and there's very, very cool floating slab design in this building to dampen out vibrations. It's sort of situated between the Mass Pike and Comm Ave, St. Mary's Overpass, you know. I don't know, 4 or 6 lanes of traffic, trains, including the T and the commuter rail. So it's kind of an impressive facility, but this talk is about retro-commissioning, sort of a holistic approach, if you will. So basically the base case of this building, we had systematic and widespread simultaneous heating and cooling. So as a director of building automation, my other quip is when I came on board about 3 years ago, everything was in a broken state, so I was really the director of broken automation. And in this building specifically, it was just a classic case of the perimeter radiation on full bore in July, August, the cooling season, and the very high supply air. And our air changes, I didn't want to be too embarrassed up here, Tom, so I dumbed it down to 12 to 16, but I did put that plus, so we might be up to 24 in certain areas. But what really happened is over time when we switched from electrical to electronic lab, to wet labs, from dry to wet, we lost the capacity of the exhaust system on half the building. The building is very redundant, typical in terms of its geometry. So you have, I don't know if this will work here, laser pointer on the bottom. Here we go. So the supply shafts are sort of east-west. This building is oriented east-west with the south facing against the pike here. So we're at no more capacity on the west side. So if thought leaders or principal investigators wanted to carve out a little nook and cranny to put in a wet bench, sorry, we couldn't do that. And I've lumped a couple of things at the bottom here. This is a very key thing in this building. We had 500, you hear that number a lot. It's a good number of devices to control things in a lab building. First generation VAV controllers. So think of 1995. These things were engineered in probably late 80s, early 90s. Extremely limited memory and very simple algorithms that were enabled here. And then all this mess was attached to network level controllers running at 10 megs. So gigabit Ethernet is pretty standard. I think university college environments are rolling out 10 gig at this point. So before I start talking a little bit about the project exactly, I've just kind of echo a couple things. John has spoken about it. Roshan has spoken about it. You come to these events and you suffer through maybe 6 hours of pontification and maybe you come away with 2 or 3 or 4 bullet points. And so the first one I want to say is that I've learned and we employed here is success at the Photonics Center is buy-in from upper management. And I know it's important for John that your upper management is here to lock, but it's also important for me to recognize that Michael Donovan is one of our VPs for real estate and facilities is here. So thank you, Michael, for attending and for showing your full support with our efforts. Thank you. The next key partner in this is it's not just about a technology or sort of money play, but really partnering with the right people in terms of safety. And our environmental health and safety folks were very good to work with. You got to remember when you're doing 20-something air changes or 16-something air changes, you start to see these linear feet per second, exceeding 100, 200, 300, and that becomes, a turbulent condition in these chemistry hoods is not safe. So they certainly were completely on board. And I think the third aspect that cannot be denied is, we need the money in place, the plan, execution, really the day-to-day coordination of laboratory access. In other words, this is retro-commissioning, right? So these spaces are occupied to the fullest. There's ongoing research. There's the academic calendar. There's grant deadlines. This is very tricky. This kind of, tough stuff here. So those are, I would say, what I would say is 3 keys for success of this project. So we started this project with a technical assistance study, thanks to our utility partners for co-funding the study. We found, with their blessing, a TA provider who was very well known in the Boston area. I can recommend them afterwards if you'd want to have that conversation. But they were very good, and it wasn't the typical RCX in terms of we'll just fine-tune everything what you have. They really did a thorough investigation of our systems and suggested some fundamental design changes. So here are some of the energy conservation measures that were identified as a result of the TA study. The first is air handler unit optimization. And I mentioned that the Photonics Center was built in a resilient and redundant capacity. So on both an east and west riser, both supply and exhaust, we have 2 air handlers, each capable, we have 4 air handlers, 2 on each side. But each air handler is capable of backing up the other one should it fail, 100% redundant. So each air handler is capable of 110,000 CFM. And so, Michael, if you're doing your math and you're saying 110 times 10 for a year, that's how much it costs to run each air handler, as far as fully AC the whole system. So it's big money, and the air handlers were not optimized. We had some at 60 hertz, others, they wouldn't move from that. Others, the fan was completely stalled. So correcting our air handlers was job one. The next bit was that the conference rooms, the associated classrooms, office, they just blasted 24/7. So our control strategy was just, let her rip. And I think the details on that, if I remember, was that the minimum set up in 1995 were about 50% of peak for your CFM on your boxes. And so we were able to quickly reduce that to 30% of peak, and then there was no schedule for the conference classrooms or offices, so they just, we just let it rip. And now in unoccupied times, those supplies shut off completely. I'm getting the hook here. So obviously lab hood and makeup air reduction. Strobic fans were a key item. Typically with Strobic fans, it's a constant volume system with bypass air. We eliminated bypass air and we installed VFDs, and we maintained to a static pressure with a safety factor for escape velocity. Off the top of my head, I think it's around 3,000 or 3,500 feet per minute. Boiler combustion controls, this is very simple, great project for everyone out there, very easy to do, O2 trim. The chiller plant design, spend a second on this. So we had a winter chiller. The chiller ran at about 10%, maybe a little more, 15% capacity all winter long to supply the laboratories, the lasers in the Photonics Center, and some other devices, some process chilled water. The chiller plant redesign enables us to now reject the heat from the process load into the incoming air handler stream. So we cool it down that way and allows us a preheat also. So those are kind of 7 and 8 there, or 6 and 7, excuse me. Since my boss is here, thank you, Michael, for coming again. I'm always reminded by upper management that we don't like to talk about money, really. We like to talk about savings. Let someone else do the math and judge us that way. But we're talking about significant electrical and gas savings, and how we were able to get to a high-performing project is really just going beyond what we typically do, which is just kind of a controls or balancing. We're really going to fundamental design changes in the chiller plant and the operation of the Strobic fans, etc. And there's certainly an energy benefit. There's certainly a carbon equivalent. But occupant comfort and operational improvements are important to everyone. And of course, for the the PIs and the folks that bring the research dollars into these buildings, having some additional capacity for future lab growth is certainly a marquee benefit. So thank you very much for your attention, and I enjoyed speaking to you later.
Good afternoon, everyone. John Kelliher. We're going to talk today about a project we undertook at Biogen, a retrocommissioning / optimization job for one of our laboratory buildings, what we call our Building 8. Building 8, some of the details, not that old building, 1999 it was built, 220,000 square feet, 100% outdoor air. It was designed to be Biogen's lab building of the future, fully flexible for whatever we might throw at it over the next 16 years and have thrown at it since then. 3 central matched air handling systems. As talked about many times today, the plug load and the internal heat load in these labs is quite high. This building is more of an analytical, technical development type building, heavy instrumentation, mass specs, HPLCs, you name it, it's in there. Typically, energy profile, I think it's Allison mentioned her proposal, this one is a beast. You can see it has pretty heavy energy demand and really was kind of our target for many years. And why we started here, a couple things. Really the number one thing, which is a little bit different flex for us, was the loss of infrastructure redundancy. While energy consumption and costs are certainly a huge thing, the thing that kept me up at night during the summer is, God, it's 98 degrees out, please don't lose a chiller today. And that's, from a facility management perspective, that's kind of a nightmare. Other reasons, obviously, largest energy consumer on our campus, 37% of total campus energy draw, even though it was only 14% of our square footage. Very conservatively designed, as I talked about in the past presentation. We started in the 12 to 16 air change rate. It worked. It was standard for the day. And really, the other reason we looked at, there are no major renovations planned. Things at Biogen never stay static for very long. If you blink, it'll get renovated in front of you. However, with this building, the next renovations are quite a few years away. So we looked at it as an opportunity here to really focus on this building, get the most bang for our buck in the short term, versus some of our older laboratory buildings that are under multi-year, multi-million-dollar renovations right now. And a lot of the things we plan to do are going to get done by default. The challenges, first time we've ever done it, relatively new endeavor for us. As Tom discussed, a costly endeavor. We pitched the proposal and they said, how much do you want to spend to do what? Are you out of your skull? The building works fine, it's comfortable, it's cool, everybody's happy, and it took a lot of persuasion, a lot of persistence in this matter to finally get it sold. Other big thing, fully occupied building, everything is in there from TD, AD, as well as GMP, GLP laboratories. Kind of a rule is thou shalt not disrupt operations, you must do it with an occupied building. And then last question we kind of wrestled with, what's the best way to do this? We looked at a couple companies out there that had done this and wanted to find, what suits our needs best, who's got the right skills to work in the environment that we have. The approach, actually kind of in the end, after many passes, kind of resembled a construction project. We engaged one of our preferred construction managers and really organized it as somewhat of a construction project with all the different trades there, your tab balancer, your BMS, sheet metal, CAD guys, that type of thing. The approach, funding-wise, was spread over 2 years, kind of conditional. You get the first wave of the funding, prove me right, prove me wrong, and then we can talk about phase 2. So it was conducted over 2 7-month windows over 2014 and 15, finished up towards the middle to end of last year. So it was kind of, we adopted and launched what we call the wave approach. Obviously, we couldn't do everything at once, so we deployed this in tiers. The first wave, assess, triage, and document. Really go through the flow. Where is it? What's broken? What's wrong? What do you need to do? Wave 2, come after that. Restore and verify. Get it back to where it needs to be. Make sure the Phoenix valves are moving. Make sure the hot water reheat valves are opening and closing. They're not jammed open. Make sure the airline's not blowing off the pneumatic valve. Kind of the operational stuff. Third wave, adjust and optimize. Take us to where we want to be. And then wave 4, come through at the end, measure, confirm, and document. One of the big things I can stress when you do these jobs is you can't document enough. The project we finished, we probably have enough binders here to fill this table right up with all the information. And it's a valuable thing, not just for any incentives that you want to go after, but to document what you did and have yourself a basis when 10 years from now, 12 years from now, you might want to be doing this again, or even earlier, hopefully. The results. So first floor 2 were kind of slow. It took us a while to kind of figure out, all right, how's this going to work? how can we do it and not disrupt the end users and get all the different trades working together. You get an enormous amount of technical trades here. First floor or two, a little bit sluggish. By the third floor we did, it was kind of just a machine. The model was laid out, everyone knew their parts and their roles. And as we kind of expected, we knew there'd be a lot of repairs. From the BMS side, the Phoenix, these were legacy first generation, or early generation Phoenix valves, analog valves, didn't have a lot of the high-end controls that they have today. They were integrated with our BMS through what's called the Midge card. Getting those was pretty hard to do. Legacy BMS, Phoenix, and then there was some skeletons. We kind of got a lot of those. Oh, you need to come over and see this today. Look at this. Check this out. Who did this? And a lot of it came to do with limited or lack of commissioning when the building was opened. We kind of expected to find some of this, and we certainly found quite a bit more than we expected. So here's kind of the money slide in terms of expectations. Really exceeded what we expected to get out of it. Obviously, we gained back a chiller redundancy. We gained back a lot of the redundancy in our fans, so that now we can actually take a fan down and have more than an hour to do maintenance. Average airflow reduction, pretty impressive, 100,000 CFM right off the top, and then you can go through with the KWH and the therms. The therms basis we convert to a steam via our CHP on site. And each phase actually received quite a sizable incentive from the utility, which certainly helped out on the payback. The payback on its own was fairly good, but as you can see with the incentive here at 4 years, it's quite impressive. This is really the first big phase. There's other phases that are in progress now. Late last year, finishing now. Phase 2 is a chill water plant. It's kind of our next target in that building. Retrofitted the chiller controls, a couple of VFDs on some of the machines. Next step will be chill water plant optimization. We know we have an issue. They have the dreaded low delta T that you always hear about in chilled water plants, and that's the next big target on our radar. And then fume hood optimization, retrofits, as time and funding obviously permits. I'd like to thank some of our partners that are up here. It was an unbelievable team effort that was a little bit unconventional out of the gate, but as we discussed by the last section of phase 2 was just a machine, and when we go to do this in another building, we're ready to go. Thank you very much.
Hello, everyone. This presentation is titled Achieving Predicted Energy Usage, and it's called that because we originally wanted to focus on the work that we just completed about 2.5 years after the building was up and operational. But as we were putting together the presentation, we realized that this story is more than what happens after a building is occupied, but it's really the story of a process that begins during the design phase and continues on through construction and on through essentially the life of the building. And after listening to the new building panel, I realized that operation and maintenance is a big part of the story that we frankly overlooked with our presentation. So this presentation is specific to the Sherman Center, but it could really be applied to any of the projects that have been discussed today. So I'm going to talk briefly about the design phase and the construction phase, and then Suzanne is going to talk about the work that we did after the building was occupied. But before I get into that, I'll just give a few specifics about the Sherman Center. It's a 512,000 square foot lab building, and it's got 4 lab floors, 4 through 9. The lower 3 floors are miscellaneous use, cafeteria, fitness center, auditorium, and classroom. It was completed in 2012 and achieved LEED Gold certification. Now, during the design phase, a energy model is completed by our sustainability consultant. As you can see, the savings were pretty substantial over the baseline, the ASHRAE baseline, 27%. And when you say 27% to a group of facilities engineers, the owners essentially, to us that means our building is sufficient. But that may or may not be so. That may not have been the spirit of the energy model in the first place, but I think that's a discussion for a different presentation. During construction, the building was fully commissioned by a third-party commissioning agent, and there was an M&V phase performed by the sustainability consultant after the building was complete. So during construction, everything was going fine. The completion date of December 2012 was really rushed a little bit, in my opinion. And we found out that after the building was completed, the process here started to break down a little bit. And we found that the commissioning wasn't completed completely. And there's a natural lag time before the completion, or between the completion of a mechanical system and its commissioning. And this interval was so compressed that I think the commissioning wasn't as effective. And the project ended. The contractors went away, and we were left with a lot of commissioning issues that were left unresolved. And the M&V effort was really not as rigorous as we had anticipated. It was more of a snapshot in time, if you will. The consultant came in and they calibrated the model to the actual building, and then they gave us results. And those results were not encouraging. We took about 6 months of data, and these are the results. The electricity was 3% high, and that sounds pretty good. The threshold that we were looking for is 5%, but this is while the building is partially occupied. So we're not really sure what that is at this point. The steam was way off. We're not really quite sure. It's gotten a lot better, and this could have been because of some faulty meter data, but it's certainly not within 5%. Chilled water was a little bit better, but still not great. So about 2 years after the building was completed, we just had a sense that it's just not operating right. Combined with this information, we took it upon ourselves to try to achieve the predicted energy performance. And we're finding that that's a hard thing to attain. And Suzanne is going to talk more about that effort.
So following the post-occupancy NMV, we decided to move forward with retro-commissioning. So we really took a three-phase approach. So first we started out with the study phase, followed by the implementation, where we physically implemented the ECMs identified, and then moved into the measurement and verification stage. And that's where we are currently. So during the initial study phase, we looked at the baseline case, which is really looking at kind of the ASHRAE 90.1 building built to those standards, compared to the proposed case, which incorporated the ECMs identified from schematic design, and then actual data from 2013. You can see we're pretty good on electricity, but steam and chilled water use is extremely high compared to what we expected the proposed case to be. So that gave us a signal that that's where we should focus our energy. And that's where we really should focus our ECMs as far as identifying ways to improve, especially with regards to steam. So we identified 4 major ECMs for this process. First, beginning with the enthalpy wheel and reducing the enthalpy wheel speed, then optimizing the enthalpy wheel modulation sequence and implemented discharge air temperature resets, and then lab ventilation, or ventilation in general. So we didn't look at lab ventilation, but we looked specifically at ventilation in the office spaces. So we reduced ventilation in the office spaces across the board during occupied hours, and then reduced ventilation in office spaces to 0 CFM during unoccupied times. In ECMs, we're about in a 1-year payback, and saved about 8.8 million kBTUs. So we had good potential for savings, and these were the 4 areas which we focused on specifically. Then we moved into measurement and verification. So this is the stage where we're currently in. So it began back in September, and it looks like over the course of the retro-commissioning, we'll save about 5.5% based on our EUI from the 2013 baseline, which is pretty good. It should get us down to about a 309 kBTU per square foot. Again, that's high. You think about where we thought our proposed case would be. We thought that would be 204. We heard a lot from the talks earlier with EUIs looking in the 100 range, and we're struggling to get kind of down to our 200, which was our proposed case. And so it looks like to date in the Sherman Center, we've saved about 9 kBTUs in the first 5 months of M&V. So we are seeing improvements, but again, it's just continuing to struggle to really look at what that baseline and meet that 204, which is kind of our goal point. But that moves us to our kind of conclusions and lesson learns, and that brings us back to this. Was 204 ever realistic? Was it a predictive model that really allowed us to kind of gauge our energy performance when the building was occupied? We haven't really explored a lot of the difference between the model that was developed and what kind of our actual building occupancy looks like. And I think that's an area for us to explore to kind of better understand kind of where we're off. Kind of, did this building conform to the model? I mean, we don't have a strong energy policy where it says we will operate this building exactly how it was designed. And again, it goes back to this kind of looking at kind of where those differences fall and how that would impact our overall EUI. Do we have accurate metering? Again, this is always a struggle. I mean, a lot of times with energy efficiency, a little blip in the metering can cause a big difference in overall analysis of the building. And then continuing with retrocommissioning, continuous commissioning, does it pay back? And we've seen that it does pay back. We've gotten significant utility incentives for this, and the paybacks tend to be under a year, which is always good when you're kind of pitching this. We are beginning to move forward with kind of looking at continuous commissioning as well, and kind of bringing in fault diagnostics, and again, reevaluating some of these building systems to really better understand how it relates to kind of our initial energy model. And that is it.
So, as Cernc R&D Boston, we had a 5-year energy plan that we had to put together, and it was to reduce energy by 30%, and that was from Global She. But so, looking at AstraZeneca, we're in 65 acres of beautiful Waltham, 6 R&D buildings, an office building, central utility plant that's almost a quarter mile away, so there's some inefficiencies there we can talk about later. About 400,000 square feet. So we started dabbling into energy reduction prior to this energy reduction measure. So in 2007, 2009, while we were building D&E building, the director decided he wanted to lower the cost of the energy before those buildings came online, so we didn't have to increase the budget. A, B, and C at 170,000 square feet, and M&N at 80,000. We incorporated nice setback strategies, changes in air temperature control, the labs and changes in labs in the offices. We formed a site energy team, which everybody knows about now. We've been talking about all day. Go and close the sashes, peer pressure, turn off the lights, and see what else we can come up with. And engineering actually lowered the inflow velocities from the fume hoods from 90 to 80 feet per minute. But how much did we save? So in all that, how much did we save? I'm actually asking that question because we don't know. We didn't have any metering. It's kind of a generalistic thing. We know the invoices are less, but we don't know where it was from, where all that energy went. So 2010 comes along, Global She says we're going to become 30% more energy efficient in the next 5 years. And so the director bid into that, and he says, okay, we can do that. I said, well, we just ended up doing retrocommissioning for these buildings. Where are we going to get all this from? And he says, I don't know, you'll figure it out. So we had the internal energy team, right? So we went to an external energy team. And that's where the local utilities come in. It's, people say this all so often, but it's the absolute truth. So local utilities, that's what they do all day. They see all this stuff. They have all these great ideas. So we worked an MOU with them, and if you don't know what that is, if you have a long-term energy plan, 3 to 5 years, you need to talk to the local utilities, and they can explain it. It's actually a great thing. We need to collect, evaluate, and prioritize ideas. Everybody has an idea, there's a lot of things out there, and we're bringing in our external energy teams. Of course, we brought in some of the best in the world, and she's sitting right across over there. The local utilities to do feasibility studies, technical assessments, and know exactly what we're going to say, because she can run the numbers like nobody's tomorrow.
I love you too, Bruce.
Thank you much. Thank you, Allison Farmer. I don't know, we couldn't have done this without you. We need to execute the plan, simple enough, but with what money? That was kind of a funny thing. And validate the savings and reinvest. So that first year, where we're going to get the money. So everybody knows that capital money is kind of more of a political nightmare, right? Everybody has capital money for the year, but they're going to use it for any particular thing. They don't want it for energy reduction, even though they're going to get it back next year. So with Allison's numbers, we could prove exactly what we were going to save. So then I could go and borrow the money from Steve Shea in the back, the director of facilities, and say, I can get you this money back because Allison says the numbers are there and we're going to do it. And it actually worked. It worked perfectly. So that way we could have the money we needed to keep reinvesting. What did we end up doing during that time? We did a bunch of projects with modified cones and exhaust systems, select airflow reductions in laboratories, free cooling optimization. That was one of the ones that Magda and Allison came up with. It saved us 100 kW right off the top, 5 months out of the year. That was a big chunk for us. Leaving chilled water temperature reset on the chillers. We did a lot of things, lighting retrofits. I took a lot of the numbers out because I told us we'd get 10 minutes and I didn't want this lady to kind of pull a hook on me anyway. So we installed VFDs. We found little stuff that we could find, data center crack optimization with VFDs on that, chilled water flow control valves, scheduling the pumps off, simple little pumps we found. Great. Night setback in the cafeteria. Why didn't we do that before? That's a good question. And daytime unoccupied modes in meeting rooms. Shut them down when nobody's in there. We know that a lot of people aren't. 2014 project, we had chilled plant optimization. And that was one of the most fun things to do because now we're saving all this money. We can now afford to go back and pull the control system out. Flow controls and we put in flow controls as an upgrade that was paid for by the utility companies. Deep night setbacks in the laboratories and offices. Supply and exhaust, reduced air change rates at 3 air changes. So we lowered the static pressure in the header, and what we found is actually a really simple thing, and I think a lot of people know about this. So we run about 2.1 inches of static pressure all day, okay? Because we need that for volumetric to get the fume hoods to work. So then we go into night setback, which we had done a few years before that. And we found we can go to 1.5 inches of static pressure. There's not that many people left, right? So you work on diversity. Because when they first balance the building, they're going to go in there, the balance is going to whip open all the valves, and you're going to say, I need 2.5 inches static pressure in the main head. Well, you don't need it at 3 o'clock in the morning. And it's very important to know. So we reduced the air exchange rates to 3 air changes an hour at night. We found we can go to 0.9 inches of static pressure in the main headers. And the great thing that the advantage to that is you have less duct leakage. Phoenix valves are going to leak, reheat valves are going to leak, so a lot of things are going to leak, but it's going to leak a lot less at 0.9 inches. So we saved a tremendous amount of air that we had to move. And during all this, because we're going through and doing all these audits, you do a building automation system audit. You're going through the labs anyway. You're doing the deep night setbacks. You have the software engineer there. But just on all of these, I mean, the incentive money that we received from the utility companies paid for quite a lot of these projects, and it kind of worked out really great for us. So when we first started out, we had a 2 meg baseline, and it would go up. And this is in the winter, so that way we can do. We don't have to adjust it any more than the simple fact that chillers aren't running. That was one of our biggest demands, right? So it's 2 megs, then it goes to 2.6 during the day. That's a simple little thing. By the time we're done, we're down below 1,300, so we're at about 1280, 1240 at times. And during the day, we go up to about 1860, so we have dropped that considerably. The nice thing about this is what we talk about consistent with a lot of times is because we dropped down from 2,600 to 800, there's 800 kW. It's also less money that we have to pay in demand charges. $22 per kW in the summertime, 18 in the wintertime. That's a lot of money right off the bat. Total lab supply. We started out about 330,000 CFM, and we dropped it down with our deep night setback at about 210,000 CF. One of those buildings, that was the M&N building, and we did that. That was the reducing it from 10 air changes an hour, 10 to 12 to 6, and that was by going in and replacing the airflow stations and dropping that down. It went from 100,000 CFM all day to 65,000, and now after the tweaks and removing a few fume hoods and really kind of getting the building together, it's 55,000 CFM. So it's kind of easy things to do, but it's a multitude of things that could be done, and going back to utility companies, a lot of utility companies have all seen these projects and they can identify them for you. One of the things we ended up doing, we put the metering in before, at the beginning, we ended up putting in an energy dashboard. That's what told us as we went how much energy we're saving. Every time we did something, we had real-time data we can go and look at. So one of the things that's going to really impact us in the summertime is a chiller plant. Well, the operators are running blind, so we gave them this little screen. And it gives them all of the units that are running, but it all rolls down to a nice little number in the corner, which is kilowatts per ton. At this particular time, this was running at 0.35 kilowatts per ton. They can select the proper chiller, the proper pumps, and actually control the leaving water temperature, and just dial the plant in. And they know when it's down at the bottom, if they're below 0.62, 0.5, they're actually doing well. If it's up around 1, someone's making trouble. It works out extremely well for them. And that's pretty much it. So we can have some questions.